Hi, welcome everyone. So let me start by introducing myself. I'm Alp Bassa. I'm a research scientist at Veridise. So shortly about Veridise. Veridise is a blockchain security company focusing on ZK applications, but we also do, of course, security assessments and audits throughout the whole stack. So our stuff comes initially, the background comes from formal verification background from academia. So basically, there are lots of researchers in our team, and that helps us also to kind of make sure the latest research results really flow into our work at Veridise itself. And as people doing formal verification, we really like tools, and at Veridise we have our own tools to kind of detect in an automated way bugs and vulnerabilities in various circuits and in systems, which becomes more and more important, as you know, as the scale of things grows. I mean, we do human efforts to audit things, but using proper tools has become really indispensable, and kind of that's our big strength, to have the good tools that you can either have us use to assess your code, or you can also use them as well if you want to. Some of our tools are available open source, so you might go on our GitHub and just experiment with some of them if you want. And if you have any questions about the tooling or the audits, I'm always happy to talk more about it. So today I will talk particularly about tools for security in the ZK domain. As you all know, like the ZK domain itself comes with its new and different kind of requirements. And I'll try to explain to you what they are and what do you need to look out if you kind of are concerned about securities in ZK applications. Yeah? So today I'll talk about how to use tools that depend on SMT solvers for the automated detections of bugs in ZK circuits. And I will particularly concentrate on a particular kind of bug, namely what we call under-constraint circuits. But of course, the same ideas you can also apply for various other sorts of bugs that you might have in ZK circuits. Yeah? Okay, so I'll be talking about SMT solvers, and we are quite passionate about SMT solvers coming from a formal verification background. And if at the end of the day I could convey to you our enthusiasm about SMT solvers, that would have been already one of the main goals of the talk being reached. So it might be technical at points, don't worry about it. I mean, I'm just trying to give you an overview. But in case you have any questions at any point, don't hesitate to ask also. Okay, so let's talk quickly about the ZK circuit workflow. I mean, I know most of you are probably familiar with, but let me just quickly go over it. I mean, programming circuits is a bit different than normal programming. It comes in two components, right? So you would write your source code in a particular domain-specific language. It could be Circom, it could be Halo 2. There are many other DSLs available. So you would write it, but then out of it, you would get two different things, right? You would have two separate components. One would be what we call the witness generator. This would be kind of the normal program that's running as you know it. But on top of that, you would have something that's called constraint generation. Yeah? So you would kind of generate constraints from your source code, right? And these would be in general just polynomial equations. And from those constraints, you can then create, using some tools, some provers and verifiers for that. Yeah? So you can kind of, from the constraints, obtain something that is, it could be succinct, it could be shorter than the program execution itself. That would be a big add-on. Or it could work in zero knowledge. So you get this additional component that is a prover and a verifier out of it. Yeah? So you have on one side the program running, on the other side you have the constraints running. So your source code will contain two parts. It will contain a computation and it will contain those constraints. Yeah? And what you want usually is that the two agree. right? So basically, let me just give you a basic example of a circuit written in Circom. So this is a very simple circuit just for demonstration purposes. It doesn't do anything intelligent. It basically has two inputs, A and B. It has two outputs, O1 and O2. Right? And what it does is O1 is just the quotient of A and B, and O2 is just the sum of the two. Yeah? But now the setup is so that the constraints, they have a very particular form. You cannot really express everything easily in terms of constraints because they have to be polynomials. There are some restrictions on the form of the polynomials. So in particular, like the first line would just take A divided by B and assign it to O1. But this is not something that you can easily translate into the language of constraints. So what you would do is you would have to rewrite this. You would say, rather than saying O1 is A divided by B, you would have to rewrite this saying that O1 times B should be equal to A. Right? So the first line would be a computation. The second line would be a corresponding constraint that you introduce. Right? And the third line is just addition. You add A and B, so that you can easily translate into a constraint because it's a nice polynomial in two variables, basically, right? So the third line would be a computation as well as a constraint. Yeah? So on the computation side, you would have one division, one addition, but on the side of the constraints, the division you would express in terms of a multiplication. Yeah? But the addition you can just write as a normal addition, right? So, and what you want is that this computation and the constraints that kind of check that computation should be equivalent. Yeah, so a valid computation should pass all the constraints, and the invalid computation should not pass the constraints, right? That's kind of what you want to have. Yeah, so you want this agreement between the computation and the constraints. So you can think of the computation as just a function, right? That takes a certain input, let's say x, and it gives you an output y. Yeah, there could be many intermediate steps, but it's just a function evaluation if you want. On the other side, the constraints, they would be given by some polynomial equations, right? So you would have all the inputs, outputs, all the intermediate values in the computation, and it would be a list of all the equalities that you need to have checked out, all the constraints that you need to check, so that kind of it captures very well the computation that you wanted to kind of prove in the end. Yeah? And one of a very common bug that happens in ZK circuits is what we call under-constraint circuits. This happens if you have a XY pair such that on input X, you don't get the output Y. Yeah? So the XY pair doesn't correspond to a valid input-output pair, but it passes all the constraints. Yeah? So then with this pair, you would pass all the constraints. It would look like a valid computation, but in fact it isn't because it does not correspond to a proper input-output pair. Yeah? And today I want to talk about how to detect these kinds of vulnerabilities. Yeah? Okay, so just to recap, it's important to have this equivalence between the computations and the equations. So basically you want that for any xy, it corresponds to an input-output pair of the computation if and only if it satisfies the constraints. Yeah? So a valid computation should pass, and nothing that is not a valid computation should pass all the constraints. Yeah? But in real life, of course, this does not always happen, and that's when you have bugs, and that's when you have vulnerabilities that can be exploited. Yeah? Okay, so how would you detect these under-constraint circuits? I mean, there's a wide spectrum of tools that you can use, and at Veridise we kind of offer tools from all around the spectrum. Some are very basic but very fast, some are very complex but need more time, and kind of you have a balance between those. Yeah? So you would have, for instance, static analysis tools which just check for certain predefined vulnerabilities. Today, I want to talk about how to use SMT-based reasoning to detect under-constraintness. And the idea is basically you can convert under-constraintness, the notion of under-constraintness, to a formula in first-order logic. Yeah, so you can write this formula in first-order logic. If this is satisfied, then your circuit is under-constrained, and then there is kind of the risk of having a vulnerability. Yeah? So it just says that there should be an input and two different outputs, such that on input X and output Y, one, you would kind of satisfy all the constraints, and input X and output Y2 should also satisfy all the constraints where Y1 and Y2 are different. Yeah? So for a given output, you should not be able to have two different outputs in general, and it can happen. This might be by construction required, but in general, this is a point that hints at there being a vulnerability. Yeah? So basically, you have to check whether this formula in logic is satisfiable. Yeah? If I can find assignments to X, Y1, and Y2, such that the truth value of this is true. Yeah? And once you talk about satisfiability, of course, you think of your undergraduate years. Maybe if you took a course where you have seen the Boolean satisfiability problem. This is the most basic satisfiability problem. So you just have logic formulas. Yeah? So you have some logic variables, P, Q, R, whatnot, and they're connected with conjunctions, disjunctions, not, and, or, and those sorts of things. And you're asked whether there's a satisfying assignment of truth values to the variables. Yeah? If there is a interpretation for this. And in this case, you can check, for instance, if you would take P false, Q false, and R true. If you put that into the logical formula up there, you would get true at the end. Yeah? So this formula is satisfiable. Yeah? This would be just a very simple logical formula, but though it is so simple, it's still the problem of automatically deciding whether a formula is satisfiable or not is very hard. It is known to be an NP-complete problem, and hence believed to be very difficult, right? And there are ways around it. You can kind of do approximations. You can do other sorts of stuff. So there are those SAT solvers which automatically tell you whether the formula is satisfiable or not. Yeah? But in our case, our constraints will not be just logical variables and truth values. They will be polynomials that you want to be satisfied. In the variables, they will take values from a finite field, right? And that finite field could be large and so on. So you basically work with a more complex structure than just logical variables, right? And that's where you come to the area of SMT solvers. So SMT stands for satisfiability modulo theories. So it is just like a SAT solver, but on top of the SAT solver, you have some additional theory. Yeah? So your formulas might involve objects coming from a different domain than just logic and truth variables. They could, for instance, have integers, they could have real numbers, they could have elements from a finite field, or lists, or strings, and bit vectors, and so on. Yeah? And then there is a big plethora of different SMT solvers with this additional theory that you want to have on top of it. So if you want to experiment with SMT solvers, the two main solvers around are Z3 and CVC5. They're both very powerful and fun to experiment with. Yeah? So in a SMT solver, you would have as input a formula in first order logic again, but over a certain background theory T. Right? So you would kind of be able to also express things in this background theory T, and the output of the SMT solver, if it works out fine, should either say, no, over this background theory, this formula is not satisfiable, or if it is satisfiable, it should satisfy it. It should say it's satisfiable and give you a model, yeah, a satisfying assignment, so to say. Yeah? Okay, just to give you a short overview of various theories that they are around, just to have fun with SMT solvers. You could say, for instance, I'm interested in expressing things in logic, plus on top of it, I want to work with integers, but I don't need to multiply the integers. I'm fine with just adding them. So that's what you get when you are doing Pressburger arithmetic, basically, right? So since you're not multiplying, you can just express linear things. And this is a very restricted theory. But the nice thing, it is complete and decidable, which means if you have a formula with this background theory, you can automatically check whether it is satisfiable or not. So there are algorithms to do it. You can decide whether it's satisfiable or not. And if a statement is true, you can find a proof for it. If it is false, you can find a proof for the negation of it. Yeah? If you make things a bit more complex, if you say, I also want to multiply the integers, then you get into the world of nonlinear integer arithmetic, right? So this is kind of the Peano arithmetic. And this is known to be incomplete, and it's known to be undecidable. So no matter how much computational power you will have formulas that you can that you are unable to decide algorithmically, right? And you can do similar things over the reals. And there's a very nice theory about the nonlinear real arithmetic going back all the way to Tarski, which says that unlike the integer arithmetic, the nonlinear real arithmetic is decidable. Yeah? So this is kind of what cylindrical algebraic decomposition and quantifier elimination and so on are all about. Yeah? So let me show you a bit the list of all possible SMT solvers that are implemented in CVC5, right? These are all the different theories that you can use. You see there's a wide spectrum of different theories that are supported. For us, mainly we will be interested in SMT solvers with the theory of finite fields and polynomials. Yeah? But just to give you, to show you how SMT solvers are in action, I just give you one example here where you want these three constraints to be satisfied, right? X, Y is a point. You want it to be on the red circle. You want it on the blue curve. And you want the X and Y coordinate to be distinct. Yeah? So the SMT solver will have its own syntax. So you will write it in the syntax of the SMT solver. Once you run it, you will get the result that it is satisfiable, and you will get a satisfiable assignment. Yeah? So you would, for instance, get this point over here, which says, OK, this formula with this theory is satisfiable, and this is a model for it. The nice thing is you also have quantifier elimination. Like if you have a statement like there exists an x such that x squared is equal to a, what quantifier elimination does is it will eliminate this quantifier there exists that you have at the beginning, right? So given a formula that has a quantifier elimination turns it into an equivalent formula that does not have any quantifiers, right? So this formula with quantifier would be satisfiable if and only if the quantifier-free formula that the quantifier elimination gives you would be satisfiable. So in this case, it would tell you, for instance, rather than checking this, you should check whether A is 0 or A is non-negative. Yeah? So A is positive. Yeah? So it's a very powerful tool, so to say. I mean, just to give you a very nice example, we all know the discriminant of quadratic equations, right, from high school algebra. If you write it as a statement, oh, there exists an x such that this equality holds, if you use the quantifier elimination, you can basically rediscover the discriminant of the quadratic equation. Yeah? If you run it, it will tell you at the end, you either want that A is non-zero and what we define to be the discriminant to be non-negative, or A should be 0, B should be non-zero, so you should get a linear equation which is satisfiable, or all A, B, C should be 0, which would kind of allow you to kind of rediscover this whole theory of quantifiers that you know. Yeah? Okay, so we will be using the theory of finite fields because our constraints will be basically polynomial equations where the variables and the constants are elements from a finite field. Yeah? And then once you want to kind of use a SMT solver, the problem is the SMT solver will kind of depend on tools from computer algebra, right, from computational commutative algebra, which are usually computationally very heavy. Yeah, so the SMT solver will have problems once your equations get larger, once your field is large. And for ZK applications, you usually have thousands of constraints, and the field that you are working over has many, many elements, right? So this is not something all the SMT solvers can really work with. So to overcome this difficulty, we devised a new tool we call PyCus at Veridise. I mean, some versions of it are open source. You can access them and experiment with them. Basically, what PyCus does, it combines the strengths of both static analysis tools and SMT solvers, right? Static analysis tools are kind of very scalable, they're very fast, but they give you many false positives, false negatives, and so on. They're not too robust, whereas SMT solvers are very precise, but they are slow. And PyCus kind of combines both of those. So what it does is it has an interactive loop, basically, where you have a static analyzer and you have the SMT tool. And first of all, one of them runs, and when it gets stuck somewhere, it gives its partial output to the other, let's say, to the static analysis tool, which will run on it. And once it gets stuck, will pass back the task to the SMT solver and so on. So with this interactive loop, you kind of get the best of both sides. Right? And using that, you can really determine, you can really catch under constraint circuits, and you can push kind of the boundary of the size of the circuits that you can analyze way further. Yeah? But then the problem is, even this hybrid approach of combining a static analysis tool and the SMT solver reaches its limits quite quickly, because the circuits are basically very large. And the underlying question is just a very difficult question. Like solving polynomial equations over finite fields have been an active research topic for many years, and we are where we are, right? And there's kind of very slow progress because it's an inherently difficult field. So what can you do in that case? What we kind of noticed is that when you work in the ZK domain, the constraints that you are working with are not the most general polynomial constraints that you would be working with in a computer algebra system. So they tend to be very sparse, right? The equations would only involve a couple of variables at a time. And they would have a lot of structure, right? If your constraints come from R1CS circuits, they would have, for instance, degree at most 2 and things like that. So then we said, okay, let's try to exploit this additional feature of the particular type of the ZK circuits and see if we can speed up things. So you really have to understand the system of constraints, and to understand that you have to kind of look at the topology of the constraints, how various variables are related to each other. So what we did is, to a system of constraints, we attach a polynomial which kind of recaptures which variables are in relation to each other, right? So for each variable, you have a vertex, and you put the edge between two vertices whenever there's an equation involving those two variables. Yeah? Once you do that, given a complicated circuit, you can attach to it a graph. Right? This would be, for instance, the graph corresponding to the FP multiply from the circuit pairing library. It has 377 variables, 392 equations. It looks quite complex, right? But you already see there's a lot of structure, right? The variables interact with each other in certain clusters, right? You have a whole bunch of variables here interacting with each other, which do not touch the variables on the other side, and so on, right? And then the aim is to kind of exploit this. And the way to do this is to kind of use the topology of this graph. You can remove multiple edges. Once you do that, you see the graph looks, in fact, quite interesting. So it has some central component, but it has some arms going out. And then you can start saying, okay, what do these arms really correspond to in terms of the constraints? And it turns out that once you look at those arms a bit closer, I'll just go quickly over this. Such an arm will, in most cases, just correspond to a range constraint. Yeah? So you would have one variable, in this case x, and you would put it in connection. You would have a constraint involving x with other variables b1 up to bk, which would basically correspond to a base 2 expansion of x. Yeah? And in zk circuits, this is the way you would express range constraints. But from an algebra point of view, when you want to express such a simple range constraints using polynomial equations, you really get a very complicated polynomial equation, which you want to avoid because the SMT solver gets stuck with it. So more precisely, if you, let's say, one variable is expressed in terms of 14 bits, right? Which would basically say it is bounded between 0 and 2 to the 14. If you want to express this simple fact, which is just, you see, just a one-line thing, if you want to express it in terms of a polynomial constraint, you would get a polynomial of degree more than 16,000, and the coefficient would be having more than 60,000 digits. Yeah, it's not coefficients of size 60,000, but the number of digits would be 60,000. Yeah? So you see why SMT solvers really struggle with those range constraints and other kinds of constraints which are not naturally expressed in terms of polynomial equations. And then we basically said, why load all of this complication on the back of the SMT solver? Let's have kind of these range constraints and bit sums, which cause in most cases, the main bottleneck. Let's have them treated separately. So we have this cooperative reasoning approach that we implemented in some of our tools that kind of has a separate module for bit sums and range constraints, and it has a usual Gröbner basis module for the normal SMT solver. And combining this Gröbner basis and non-Gröbner basis approach and exploiting the graph structure, you can see that the boundary of circuits that you can hunt for, under constrained circuits for, you can really push it way further. Yeah? So you can kind of things that were previously totally out of reach, you can very easily now resolve in these cases. Yeah, that's all I wanted to tell today. So basically, I tried to just give you an overview of what SMT solvers do, right, and why they are so powerful, but what their limitations are. But I try to kind of show you, hint at least, at how to circumvent those limitations. And if you want to see all of this in action, please go and experiment with our tools. And I'll be happy to talk about audits or tools after offline if you want to. Yeah. Thank you.
Thank you very much, Alp. Maybe just a short question if we can take, if anyone has. We're just making here one question.
Thank you. Thank you for the talk. I was wondering, you mentioned this interactive dance in the tool that you showed between static analysis and the SMT solver. And you said that when one gets stuck, the other one picks up, the output and continue with it. But static analyzers are known to have false positives. Do you always verify the result of the static analysis with the SMT solver? And if that's the case, does that eat into, the runtime?
I mean, yes and no. I mean, you're right. Like the static analysis will have many false positives, right? It would bug you all the time with saying, oh, here there might be something, here there might be something. So you really have to watch out what you pass from one to the other, right? So this was just a very broad overview saying, okay, you have only those two. But like the static analysis could tell you that, for instance, some variables are deterministically determined without having any false positives or negatives, right? So you have to really, you combine two different worlds, and you have to be careful which parts of those two worlds you really let interact, because we want to have the positives of both sides. If you do it the wrong way, you can get the negatives of both sides, where you get many false negatives, and the SMT solver gets stuck all the time. So you really, this was just a very broad overview that fits inside here, but it's also published as a research result. So if you want to have a closer look at it, you can find all the references on the Veridise webpage to it. Yeah. Thanks for the question, though.